Welcome to this presentation of Describing System Behavior. My name is Will Goodwin, and I'll be your instructor. If you have any questions about any of the information covered in this presentation, please use the question and comment box. This module is going to discuss the following. How do we model the interaction of multiple objects working together? We're going to see how we can use sequence diagrams for depicting this behavior of objects, cooperating objects. We'll also mention communication diagrams, but explore them in more detail later. First of all, object interactions. An object-oriented programming language program is designed to rely on objects which communicate with one another. One object can invoke a method on another object, passing parameters in that method, and possibly obtaining a return value from the method that was invoked. It's pretty common. Objects are designed to work together to provide the functionality of our system. And that functionality, we're suggesting, should be described originally in a use case. Now, while class diagrams are very useful, and that's why we spent 3 modules discussing the various aspects of class diagrams, they simply provide a static view of the kinds of objects that we'll encounter in our program. They don't really tell us how those objects work together to do any kind of behavior. Even though we have the operations defined in the classes, there's no indication of when those operations are used or who sends those operations, who invokes those operations. How do the objects work together? For that kind of picture, for a dynamic view of how the objects will work together, we need a totally different kind of diagram. And it turns out interaction diagrams are the answer to our question. There are several different kinds of interaction diagrams, but they're all designed to provide some kind of dynamic view of our system and the behavior of the objects communicating together to implement those scenarios that are described in the use cases. An interaction diagram, again, is going to focus on how objects are going to work together, and the functionality that they're providing is going to be coming from a scenario described in a use case. And if you remember, the use cases had actors associated with them. The actor is typically invoking a use case, starting a scenario. That's what's going to happen on our interaction diagrams as well. Sequence diagrams, the ones that we're going to explore in this module, have a vertical time axis, which makes it very easy to indicate the ordering of the messages. And communication diagrams are designed to emphasize the links between objects. They can depict the same kind of interaction that a sequence diagram can. Each object in a sequence diagram has a lifeline that indicates the existence of that object and how it's going to be available and when it's going to be executing. Messages are sent to an object, and those are represented by an arrow, and we can label that arrow with the message name and parameters and return type and so forth. An activation bar, which sits over the top of the lifeline for an object, represents the period of time when that object is actively executing the method that was invoked by the message arrow. Here's an example of a very simple sequence diagram. Our customer actor is starting things off by choosing a particular item. And the item, in its choose operation, then invokes the add item method on the invoice. So now we have the actor starting it, and we have 2 objects communicating together. Communication diagrams also emphasize how objects work together, but unlike sequence diagrams, they don't have a vertical time axis. Their organization is totally different, and they emphasize the links between objects. And if you're interested in emphasizing when a new link is established, when one object obtains the identity of another, you can do so on these kinds of diagrams. And you can also indicate when new objects are created. You can also do that on sequence diagrams, as we'll see a little bit later. The requirement on communication diagrams is that in order to send a message, there must be a link going to the object that you want to send the message to. So the links really represent communication pathways. You have to establish the link before you can send the message. But the big problem on communication diagrams is what is the order in which these messages are being sent. There's no time axis, so there's no time ordering that way. Since there's kind of a free-form layout for message placement on a communication diagram, we have to resort to a numbering system. And because when one message is sent, it may send a message to another object, there's a dotted notation employed to represent that hierarchical structure of our message sending. For example, here's the same scenario as we saw in the sequence diagram, only now it's represented on a communication diagram. Our customer actor, again, is choosing an item, and now the item is sending the add message to the invoice object. Notice the numbering. Number 1 starts things off, and message number 1.1 is the first message sent from within message number 1. So when we go to use a sequence diagram to model some of the behavior in our system, we should have a particular scenario in mind. We don't just sit down to say, oh, I think I'll make a sequence diagram. Rather, you'll say, I think I need to make a sequence diagram to emphasize this particular scenario from a particular use case. So you'll need to identify the actor that initiates this scenario, probably the primary actor involved with that use case, although maybe not. And then you need to identify the objects that are going to participate in this scenario and identify the messages that are sent. And eventually, although maybe not initially, the information that is passed, the parameters that are passed, the return values that are sent back. So what can you put on a sequence diagram? Well, actors that start things off, objects with their lifeline that extends down below them, and the activation bar that indicates when they're actively executing a method. Classes could appear on here if we have any class scope operations. And the messages represented with the arrows, and you can put in, besides the message name, a parameter list and return type. So when we go to send a message, this is represented as an arrow, the arrow pointing to the object that receives the message that should actually execute a method for us. The arrow always points from the sender to the receiver. And the order of the messages is indicated by top to bottom order. We have this nice vertical time axis. This is one of the strengths of the sequence diagram. So here we have an example of a sequence diagram, and notice that we have two distinct types of arrowheads here. Notice we have just a little stick arrowhead here, and here we have a filled-in triangular arrowhead. This is again an example of where the Unified Modeling Language is very precise about their arrowheads. They both represent a message being sent to an object. But the asynchronous message, the stick arrowhead here, represents the message being sent to an active object, our command processor, whereas the filled-in triangular arrowhead represents a synchronous message being sent to a passive object. If you remember, the passive object executes in the thread of the caller, whereas the active object has its own thread of execution. One consequence of a synchronous message is that the sender of that message must wait. It blocks while the method executes because that method is executing in the caller's thread of execution. So the sender will block while the method executes. Also, it's quite often useful to have an object send itself a message. It can invoke one of its own operations, and in fact, if you think about it, a private operation, which is certainly legal, could only be called by the object itself, because it would have to be called by code within that same class. Quite often you'll have a private operation that will be invoked from a public operation. The private operations then are not exposed to the outside world. They could be utility operations or things like that. Here's the notation for a self call. We have two of them actually. One here, open connection, and then close connection. Notice the arrow just bends around, comes back, points to the same lifeline, and you'll notice the activation bar, the small activation bar, located on top of the original activation bar in both cases, indicating that yes, the database access object in this case has one of its own operations. The OpenDB connection is being invoked from within the query database. We've also indicated in this diagram that we don't really care who is going to send this query database message. It's most likely not an outside actor, because this database access object is probably not one that would communicate with the outside world. It could be that we just don't care, or it could be that there are several different kinds of objects in our system that could do this. And what we're trying to depict on this diagram is simply the interaction between the database access object and the query object. Quite often, as a scenario is unfolding, new objects need to be created. When we do this on a sequence diagram, we'll add in the object box at the point of creation, that is below the top line of our diagram, to indicate this is the point at which the object was created. Now, objects that are already in existence when this scenario started always appear at the top of the diagram. So this is a pretty clear and explicit way of indicating which objects are already in existence and which ones are newly created during the execution of this scenario. Now here's an example of our child artist actor being creative and creating a new shape, creating a wiggly worm. Notice the wiggly worm object box is below the actor and below the picture object. And the UML defines that the create message should be a dashed arrow with a stick arrowhead. Now once the shape has been created, then the child artist indicates they want to add that shape to the picture. It's a tough life being an object. They get used, and then when they're no longer needed, they get discarded, deleted, removed. We can indicate that also on our sequence diagram. Their lifeline terminates, and at the end of the lifeline is an X. It's an inglorious end to an object. But it certainly is explicit in marking the end of an object's lifeline and existence. Once again, our child artist is at work, and they've decided that they don't want that jelly blob in their picture anymore. So they're sending a message to the picture object that they want to remove the selected shape, and the picture object then is sending the destroy message to the jelly blob. And you'll notice that's it. The jelly blob is no longer in existence. That object is now no longer in our program, and obviously it's not in the picture anymore either. So given that information, you're all set to model an object interaction with a sequence diagram we are going to give you the following scenario. It's up to you to decide what objects are involved and what messages should be sent. So here goes. We have a pet owner who goes online to update her profile. She wants to add her new cat, Sunspot, and her new dog, Fido, to her collection of pets. We're describing this as the sunny day scenario. We're not expecting any problems. We're not going to deal with any problems or error conditions or anything like that. Assume that everything goes swimmingly. So your task is to create a sequence diagram for this particular scenario. Go ahead and take some time to do that. When you're done, come back and we'll take a look at a solution and have a short discussion of that. Welcome back. Here's our pet owner starting things off, and they're indicating they want to add a new pet to their profile. Notice their profile object is in existence. They're adding a new pet. Well, the first pet they're going to create is the cat, Sunspot. And then we go ahead and they say we want to add another pet. We want to create the dog, Fido. So you notice that we've got dog and cat objects created, and a confirm update is sent back to the pet owner to give them assurance that their changes have been actually recognized and implemented. So in this scenario and in this sequence diagram, as I mentioned, the objects, the dog object, the cat object are created and appear at the point of creation. The pet owner profile object was already in existence, so it appears at the top of the diagram. And the confirmation message, the reassuring confirmation, is sent back to the pet owner. Of course, your sequence diagram may have been different. That's quite all right. What we're doing here is modeling our vision of how the system is going to be created and how the objects are going to work together. So what we've discussed in this module is how we've started to talk about how to model object interactions, a dynamic viewpoint of our system, and how to use sequence diagrams to depict behavior. We have other types of object interaction diagrams, and we'll discuss those in later modules. If you have any questions or comments about the information covered in this presentation, please use the question and comment box. Hey, thanks for joining me.